Okay, here we go. Many employers require prospective employees to take a drug test. A positive result indicates the prospective employee uses illegal drugs. However, not all people who test positive actually use the drug. So suppose that 4% of prospective employees use drugs. The false positive rate is 5% and the false negative rate is 10%. A randomly selected prospective employee tests positive. What is the probability that he actually took the drugs? Okay, so we've got employees. And we have two possibilities. Number one, they are taking drugs. Number two, they are not taking drugs. And so if they are tested, they can get a positive result or a negative result. And same thing right here. So it says,
do it so employees and positive and then drugs.
no, it's gotta be this first. Okay. So his question was, could you reverse those? And no, because we want to know what's the probability that they test positive, given the fact that they are or are not using. Okay, so the probability that they're taking drugs, it said it was 4%. So this is going to be 0.04. And so this would have to be 0.96. And so if they test positive and they are actually using, then that's correct. However, if they test negative and they are using, this would be a false positive. Okay, and so here, if they test positive, but they are not using, hold on, I wrote that wrong. Sorry, 1 second. Stop. Let's try that again. This would be a false negative. There we go. Now we're in business. Okay, and so likewise, if they test positive, however, they are not using this would be the false positive. Okay, so they asked, what is the probability that they actually took drugs, given the fact that they test positive? So we need to find the probability that they test positive. Okay, that's a conditional probability. So we're going to multiply this times this percentage. And so it says in the stem of the problem here that the false positive rate is 5%. So that means this right here is 0.05. And so the complement of that would mean this would be 0.95. And the false negative rate is 10%. So this would be 0.10. And therefore this would have to be 0.9. So what's the probability of a positive test? Well, there's two different outcomes where they have a positive test. Right here and right here. So given the fact that this is a conditional probability, I'm going to multiply 0.04 times 0.9. And that gives me, what's that, 0.036. And so that's one possibility. The other possibility here is that they get a false positive. So they're going to do 0.96 times 0.05. So take your calculator, plug that in. And that should get half of 96 is 48, so like 0.048. So these two outcomes, this positive and this positive, are mutually exclusive because it's not possible to happen at the same time. So I'm going to add these two things together. So 0.036 plus 0.048. Add that together. And when I add those two things together, you should get 0.084. So that is the probability that you get a positive test. And so the question asks, what is the probability that they actually took drugs given the fact that they got a positive test? So conditional probability, we saw it 2 days ago. Conditional probability is always intersection over condition. So I want the probability they took drugs given the fact that they tested positive. And so that's going to be the probability that they took drugs and tested positive divided by the probability of a positive test. Okay, so what's the intersection? They took drugs and they tested positive. That's going to be 0.036 right here. Divided by the probability of a positive test, which is this number right here. So I've got 0.036 divided by 0.084. Put that into your calculator. And what do we get? Okay, 0.429. So there is about a 43% chance person with a positive test actually took the drugs. Let me go down here. With a positive test actually took drugs. I would think we would want that to be a little higher. Okay, and so that leads us to this, which is an important concept in probability. Two events, A and B, we say they are independent if the occurrence of one event does not change the probability that the other event will happen. In other words, events A and B are independent if the probability of A, given the fact that B has already happened, is equal to the probability of A. In other words, B did not affect the probability of A. And the probability of B, given the fact that A has already happened, is equal to the probability of B. So for example, let me give you a quick example to illustrate that. Let's say I draw a card from a standard deck of cards. What is the probability that I get a heart? It would be 13 out of 52 or 1 out of 4. Well, let's say I draw a second card. What's the probability that I get a heart on the second draw? Well, that depends if I put the card back or not. Because if I don't put the card back, number one, there's one less card. So I'm dividing by 51 instead of 52. Number two, it depends on if I drew a heart the first time. So it could be 13 out of 51, or it could be 12 out of 51. So the probability that I draw a heart on the second draw depends on what I drew the first time. Therefore, those two events are not independent of each other. That makes sense. However, if I draw a card with replacement, so I draw a card, what's the probability that I get a heart? 1 out of 4. I put it back, I shuffle, I draw another card. What's the probability that I get a heart? Now it's 1 out of 4 since I put it back. Also, therefore, those two events are independent, and the first draw did not affect the second draw. That makes sense? Okay, so turn the page and let's look at an example. Is there a relationship between gender and relative finger length? To find out, we use the random sampler at the Census at School website to randomly select 452 US high school students who completed a survey. The two-way finger shows the gender of each student and which finger was longer on their left hand, either the index finger or the ring finger. So quick little check. Look at your left hand. Raise your hand if your index finger is longer. Raise your hand if your ring finger is longer. Surrounded by weirdos, right? Raise your hand if they are the same length. Okay. So this says, are the events female and has a longer ring finger independent? Justify your answer. So we want the probability that the ring finger is longer, given the fact that the person is female. So this is a conditional probability. Intersection over condition. What's the intersection of ring finger and female? Going to be right there, which is 82. Given the fact that they are female, so they must be female, so we are just looking at this column. So I have 82 divided by 212, which is 0.387. And so now I'm going to find the probability of having the ring finger longer. So look back at this formula. At this formula right here. The probability of A given B equals the probability of A if the events are independent. So if these two events are independent, then the probability that the ring finger is longer should be the same as the probability of the ring finger being longer, given the fact that they are female. Because if that's true, then the fact that they are female does not affect the probability that the ring finger is longer. Does that make sense? So let's check that. What's the probability that the ring finger is longer? We're looking at the total number of people that have a longer ring finger, which is 234. Divided by the total number of people surveyed, which was 452. And this is equal to, it's a little over half, right? 0.518. Therefore, since these two probabilities are not equal, the events are not independent. Because the fact that they are female affects the probability that they have a longer ring finger. Yes.
So like when a question asks you to explain or justify why two events aren't independent, you can write out their probabilities and just say these aren't equal, so they wouldn't be independent of each other.
That's correct. There's also another formula to use that you can check to see if they are independent.
Oh.
Yes,
Do they have to be like exactly equal, or can it just be
Yes.
close?
they have to be exactly equal. Otherwise, they're not independent. Because their probability is affecting one probability, the first probability is affecting the second probability. Okay. So And so that leads us to this rule. It is the multiplication rule for independent events. This only works for independent events, but it says the probability of A intersection B equals the probability of A times the probability of B. This must be true if the two events are independent. So you are not old enough to remember this, but I remember it. I was in 6th grade. They did, I don't know if it was a contest, but for the first time, they selected a teacher to go up into space. And so that teacher went through all of the astronaut training. There were actually 2 that were selected. There was a backup. They selected 2 teachers from a national process. They went through all the training at NASA, and then that teacher went up with the 6 other astronauts. Okay, in 1986, they launched from Florida in January of 1986, and it was unusually cold that day, and there was a tragic accident. Space shuttle exploded shortly after takeoff and killed all 7 people on board. There's a really good documentary on Netflix if you're looking for something to watch this weekend over your 4-day weekend. Okay. So following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under the cold conditions that day, experts estimated that the probability that an individual O-ring joint would function properly was 0.977. But there were 6 of these, and all 6 had to function properly for the shuttle to launch safely. Assuming that O-ring joints succeed or fail independently, we'll find the probability that the shuttle would launch safely under similar conditions. So if they are independent, then we are going to multiply the probabilities together. So the probability that the first O-ring joint functions properly would be 0.977 times the probability that the second one functioned properly would be the same. All the way 6 times. Okay, so I'm gonna shorten that. I could write this as 0.977 raised to the 6th power. And so what is that? Put that into your calculator. So there was about an 87% chance the shuttle would launch safely. Under these conditions. Okay. So again, if you're in charge of the mission, go or no go? Is 87% high enough for you? It's not for me, right? 13% chance that everybody's killed. I would abort the mission and wait for better conditions, right? But this was done after the fact, obviously. The point being here, if they are independent, we are going to multiply their probabilities together. Okay, so turn the page for me here. We got one more page. So this says the first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine, approximately 5% of normal pregnancies will receive a positive result. if 100 women with normal pregnancies are tested with a first trimester screen, what is the probability that at least one woman will receive a positive result? Okay, well, first, we must establish independence. So it is reasonable to assume test results for different women are independent. Okay, so number one, you must establish independence either by it is given to you in the stem of the problem, or you can reasonably conclude that it is true. So this is why this problem is in the notes. The probability of at least one probability of at least one is 1 minus the probability of none. In this case, the none refers to no positive results. So think about this. We test 100 women. How many positive results could I get? Well, there could be 0, there could be 1, 2, 3, all the way up to 100. So what is the probability that I get at least one positive result? Well, you could add all of those together, right? Or since the probability of all of them together is 1, I'm going to do 1 minus the probability that none of them tested positive. Does that make sense? So what is the probability that a single test is negative? Probability of single test negative is 1 minus 0.05 or 0.95. So now what is the probability? All 100 tests are negative. Okay, it would be 0.95 raised to the 100th power because we established that they are independent of each other. So put in 0.95 raised to the 100th power. And we get, that should be like 0.0059. Okay, so the probability, this is the probability that none of them have a positive test. So to find the probability that at least one of them has a positive test, we're going to do 1 minus this probability. So probability of at least 1 is 1 minus 0.0059 or 0.9941. Okay, so there's over a 99% chance that one of the women tested will get a positive result for chromosomal abnormalities. However, their pregnancy is considered normal. Okay, so if we were doing this for reals, right, they most likely would have her tested again, okay, to confirm it. since there's a really high probability, if these are accurate, that she's going to test positive, however, it is a normal pregnancy. So they would do it again, because the probability of 2 positive tests in a row when it's normal would be extremely low. So they would do another test to confirm. Okay, so a couple more here quickly. Suppose that for a group of consumers, the probability of eating pretzels is 0.75, the probability of drinking Coke is 0.65, and further suppose the probability of eating pretzels and drinking Coke is 0.55. Determine if these two events are independent. So if they're independent, again, according to that formula, we know the probability of pretzels and Coke together, the intersection, that's the probability of A intersection B, must equal probability of A times the probability of B. So here's a simple check for independence. The probability that they eat pretzels is 0.75. Probability that they drink Coke is 0.65. And the probability of both, the intersection, is 0.55. So we do 0.55 and we check to see if that is equal to 0.75 times 0.65, and it must be exactly the same. And in this case, it is not. Therefore, these events are not independent. 3 dots mean therefore. These events are not independent. So the probability that a new tire will have a blowout in the first year is 0.1. If 4 tires on a new car function independently of each other, what is the probability that at least one tire blows out in the first year? So anytime we're calculating the probability of at least one, we do 1 minus the probability that none, which in this case is no blowouts. So I'm going to do 1 minus, what's the probability that I have no blowouts? Okay, the probability that I have a blowout is 0.1, so the probability that I don't would be 0.9. And there are 4 tires. So we do 1 minus 0.9 raised to the 4th power, which is 0.3439. So there's about a 34% chance that we do have a blowout in the first year, which again, for me, a little high. And finally, it says a family is going shopping for a new van. The probability that the family will purchase a Ford van is 0.33, a Chevy van is 0.25, a Dodge van 0.2, and a Toyota van 0.22. What is the probability that the family purchases a Toyota van or a Ford van or a Chevy van? Okay, well, we are assuming we are not buying more than one car. Therefore, these events are or mutually exclusive, or we would say disjoint. Okay, and so if they are disjoint, we are going to, how do we calculate the probability? We add them together. So the probability of a Toyota is 0.22. Plus the Ford is 0.33, plus the Chevy is 0.25. And we add all of those together and we get 0.8.